All right, so we're going to spend the next couple days talking about mass spectrometry. Mass spectrometry is one of the most useful analytical tools that organic chemists have at their disposal. If you guys ever watch CSI, they kind of take it to a level above and beyond what's actually going on. In CSI, they'll take like a paint sample and they'll be like, this was bought on Thursday from the Lowe's down the street. The checkout cashier was named Nancy. That's not really how it works, but it tells you detailed information about how heavy your molecules are, which is incredibly useful as a chemist. So let's kind of go through the most basic demonstration of what happens with mass spec. So let's say we've got this carbon-carbon bond. Essentially what we'll do is we'll take an electron source and we'll actually bombard this bond, right? So I'll add an electron beam. And what happens is that these electrons almost play billiards with one another. You can eject another electron out of a bond. And when you do this, you form what's called a parent ion. So in this case, we've ejected one of those bonding electrons, which will give this compound a positive charge. And then you have this ejected electron that got kicked out from that electron beam. And what this is called is a radical cation. It's called a radical because it's got a spin unpaired electron. And then obviously it's a cation because it's got a positive charge. And oftentimes when we're talking about this in terms of mass spec, this will be referred to as our parent or molecular ion. This is one of the most useful ions that we look at when we're doing mass spec because it will tell us the weight of our molecule minus one electron, right? What happens next is that this will quickly rearrange because this is very, very unstable, and it will rearrange into a radical, and it will rearrange into a cation, right? So if we were to draw this using our arrow notation, essentially that electron would pick one side to hop over to, and we would have one carbon left without any electrons, giving it that positive charge, and one carbon with unpaired electrons. So now we've got our radical, we've got our cation. And essentially what these are called are just fragments, right? So when we do mass spectrometry, we're actually bombarding our molecule with electrons, exciting it up to a radical state, and then it quickly falls apart into a bunch of fragments. And these fragments are also very useful tools that we can look at. In particular, chemists like to study these cations. So mass spec looks at cations. And why are these cations so useful? Well, we can do some fundamental physics with them. So let me actually move these down. So let's take a look at the physics that we can do with these. Let's say we've got our cation, and I'm just going to draw it as our generic plus molecule there. And this is flying through a stream of helium gas. What will happen is you can actually send this through a detector, or a magnetic field, excuse me, where you can have one side of the field have a positive charge, the other side have a negative charge. And all this is basically just a magnet, right? Do you think that cation will be deflected? Will it go straight through? Will it go up? Will it go down? What will happen to it? It'll go down, right? Because if we think about the positive charges, they're going to repel each other, and it's going to be more attracted to that negative charge. So we can think about this, and we could say, well, if it was going straight through, it would have just gone like that. But in reality, it'll get deflected downwards. When it does this, it'll go through and hit a detector. And so basically what chemists do is they measure how far this deflection was. Obviously, the more charge it has, the more it will be deflected. and then the lighter it is, the more it will be deflected. So we can directly look at mass, and we can look at charge on our molecule. The actual equipment setup is a little too complicated for me to draw, so I copied the picture from your book. And if you look at it, the same idea applies, right? Let me grab my pen. We enter or inject our sample into essentially a molecular heater. It will heat up your molecule in order to vaporize it. Once it gets vaporized, it goes through and there's an electron source that will bombard your molecule with electrons, forming that radical cation. Then we use this gas beam to essentially target our molecule really, really closely to this magnetic field so that we can look at the deflection through the magnetic field, and then it hits a detector. The mass specs that are used today range from around $10,000 all the way up to $1 million pieces of machinery that are used to look at biomolecules like protein and DNA. So the mass spec we'll be talking about today will be primarily the most rudimentary mass spec, but just know that if you go into biochemistry or any other advanced chemistry field, you'll be using mass specs that are far, far more sensitive. So when the sample comes out and hits this detector assembly, a computer immediately processes that data, and what it does is it gives you a mass spectrum that might look like this. So this is an example of methane. So if we think about methane, methane should weigh what? 16, right? So carbon weighs 12 roughly, each hydrogen weighs 4. So if we look at this, we've got our biggest peak at 16. And this is our parent or molecular ion. And another designation that people use to talk about this is they just say M for the parent, and then they do dot for the radical, and then plus for the cation. That basically indicates the mass of your peak, right? It's going to be the heaviest one, obviously. Anything smaller than that's likely going to be a fragment. One thing I want to ask you guys is, what's this little peak that's showing up right above? Why would we have some of our molecule that weighs 17? Yeah, if we think about Gen Chem, we talked a lot about isotopes, right? So we have carbon-12, but there's also a little bit of carbon-13 around. So what this is called is our M+1 radical cation, and these are due to heavier isotopes of things like carbon or halogens or any thing that has a heavier isotope will have a little peak right above it. But we're primarily interested in the peak that has the highest intensity here at the most at the highest charge to mass ratio region. Basically anything in this region, what do you think these are? They're fragments, right? So we're blasting off some sort of hydrogen, and when we're doing that, we're forming maybe a methyl radical or some other higher order radicals here. So we get fragments. It's important to remember, too, that if we look at this chart, we've got relative abundance. This can be scaled to whatever you want it to be. It's all just relative, right? We're comparing one peak to another peak. So it's just a ratio of peak sizes. The other thing to remember from these charts is that if we look at, I'm going to move this line a little bit. If we look at the units here, the units are in M to Z. And this is in a mass to charge ratio, right? Usually the charge on our molecules is +1 because we ionize it once, so we'll form one cation. But theoretically, you can actually form a double cation where you've got two cationic sites, in which case it will be deflected twice as much down into your detector, so that will change the fragmentation peaks as well. Usually, though, what we're looking at, though, is a charge of +1. Oop. So the M to Z equals Z. Oops, sorry, equals mass. And the mass that we get out of here is calibrated to be in AMU, or atomic mass units. So it's directly correlated towards our molecular weight, right? Are there any questions with the overall setup? All right, now let's do a little bit more digging. And in particular, what I want to do is focus on this parent molecular ion, because this is the most useful ion that we get out of it. It tells us the mass of our molecule, right? So that tells us a lot of useful information. So let's take a look back at our peak. We said that if we have methane, that this is our radical cation peak, right? And we've got that M+1 peak over here. And this is a radical cation, and then we've got fragments over here. Are you ever going to have heavier fragments than your parent fragment? No. Usually entropy says if we're going to slam something and destroy it, it's going to go to smaller pieces, not bigger pieces. Same idea of throwing a bomb into a building. You're not going to get a newer, bigger building. You're going to get a building in fragments, right? So in this case, fragments will always be lighter. And typically when you get this data, you can actually look up this relative abundance or relative height of your peaks, and this is very useful specifically when you're looking at isotope patterns, and we'll talk about that next. But look, yep.
Does it matter how we write it? Because there you have the M plus the logotony, but each time you've been writing, you write dot plus.
I don't think it really matters. When you say it, you always say radical cation, so I do dot plus, but in the book they do plus dot. Yeah, it doesn't really matter. Tomato, tomato. All right, let's look at pentane, which is a little bit more complicated. What's our parent peak going to be at for, or what's our parent peak going to be for pentane? So let's think about how many carbons and hydrogens we've got there. We've got C5H what? See, we've got 3, 6, 8, 10, 12. So C5H12. If we do the math, 5 times 12 is 70 plus 12. Oh, wait, no. 5 plus 12 is 60 plus 12 be 72, right? So if we look at this, we've got a peak at 72. This is equal to our radical cation peak. And this tells us our mass of our molecule. What's going on to the left of it? Why do we have all these other peaks? Yeah, we're breaking things, right? So if we look at this one, it looks like we've gone from 72 down to 57, right? So what's going on there? We've lost 15. What weighs 15? Yeah, we've lost a methyl radical, right? So if we look at this one, we can actually go through and we can figure out what these fragments are. So if we lost a methyl radical, it had to have come from one of the ends. So this peak over here corresponds to this cation. What about this peak right here? Yeah, we've lost another methyl group, right? So we've lost another group. If we look over here, this is now our ethyl cation. And then if we look over here, we've got our methyl cation. So oftentimes the relative abundance of these peaks is directly correlated to how stable they are, right? We know of different ways to stabilize carbocations. Those peaks will be a lot more stable, they'll exist a lot longer, and they'll show up at a higher intensity in your detector. So more stable carbocations show up more intensely. So So for the problem of the day that I gave you, it's up to you guys to figure out what can maybe stabilize some of these carbocations, and you guys have to do some intuitive reasoning there. Yep. No question? All right. So let's take a look at another trick that's really, really useful for the radical cation peak. If you look at carbon-containing compounds, we're always adding carbons, which are average weight of 12, and we're always adding hydrogens in sets of 2s. So is our mass going to be even or odd normally? Even, right? So this is a really useful trick. So if we're thinking about a hydrocarbon, in this case, I'll just use pentane. It's got a molecular weight of 72, and it's even. All right? What if we switch this last carbon to an amine? Well, then our molecular weight goes to 73. 73. So now it's odd. What if we decide to make this compound really stinky and have it be a diamine? Then it goes back to a molecular weight of 74, and it goes back to even. Essentially, the trick is anytime you see an odd number for your parent peak, that means you've got one nitrogen in there, right? If it's an even number, it either means that you don't have any nitrogens or that you've got an even number of nitrogens. So odd radical cation is a hint that there are an odd number of nitrogens. We're pretty lucky as organic chemists because really when we do mass spec, we're only dealing with a handful, like 5, 6, 7 atoms. If you go into inorganic chemistry, this rule is essentially thrown out the window because you're dealing with transition metals and a lot more of the periodic table than we're looking at. But this is a really useful trick for organic chemistry. Anytime you see an odd number, think nitrogen. Nitrogen's probably involved somehow. All right, let's take a look at that mass plus 1 peak because it's also very useful. It tells you a lot of information without really being that big. So let's look at the m plus 1 peak there. And we said that that m plus 1 peak is due to heavy isotopes, right? Is due to heavy isotopes. So let's think about the most common atoms that we're going to run into in organic chemistry. What's the most common? Carbon, right? So if we think about carbon, the most common carbon is carbon-12. Carbon-12 has an abundance. I'm going to make a chart. Carbon-12 has an abundance of 98.9%. If we look at carbon-13, it has an abundance of about 1.1%. So that means out of every 100 molecules, roughly one molecule of something like methane will have carbon-13 in it. The other 99 will all be carbon-12. It's just its statistical probability, really. What's another atom we run into a lot? Hydrogen. So let's look at hydrogen. If we look at hydrogen, hydrogen is 99.99% regular hydrogen. If we look at deuterium, where it's got that extra neutron, this exists in 0.01%. So really, really tiny probability of running into a deuterium compared to a heavier isotope of carbon. What's another one? oxygen. So let's look at oxygen 16. This will be 99.63% O16. If we look at O17, this will be 0.37%. So again, really, really tiny probability of running into a mass plus one peak for oxygen. It's going to be a very tiny contributor. The last one is nitrogen. So nitrogen is normally 14. This will be, oops, let me fix this number. I've got these flipped. Sorry, guys. For oxygen, it was 99.96, and then O4. And then for nitrogen, it was 99.63%. And then for nitrogen 15, it was 0.37%. So if we look at the main contributor for the mass plus one peak, which atom is it going to be? Is it going to be from deuterium? Probably not. It's really, really tiny probability. If oxygen, also really tiny probability. Nitrogen, a lot less so. But what it's really useful for is a reasonable probability of finding carbon-13. The rest of these over here, whoa, sorry. Hopefully it comes back here. The rest of these are fairly negligible. My computer spazzed out on me. Reasonable amount of carbon-13. Am I spelling negligible all right? I'm gonna say yes, hopefully. All right, so we've got a reasonable amount of carbon-13, and this is really useful, right? So if we've got, let's say 1.1% of our sample is showing up at that M+1 peak, that means that there's one carbon atom in the molecule, right? What if it's 2.2%? How many carbon atoms are in our parent molecule? 2, right? We've increased the likelihood by 2. What about 3 carbon atoms? And it'll go to 3.3%. So this is a really useful tool for determining the number of carbon atoms that are within our parent molecule. So useful for determining number of carbons. So let's think about how we can do this. We can actually turn this into a math equation. Don't worry, it's not calculus level. It's like, can you divide? Hopefully you guys can divide. So if we look at our number of carbons, what we should do is take our M+1 radical cation intensity and divide that by our parent intensity. I'm going to multiply this by 100 and divide it by our 1.1% abundance of carbon-13. So this is a really useful tool, right? So let's go through and do some examples of using this. So let's say that we've done mass spec and we found a radical cation parent peak at a mass to charge ratio of 68, and its relative intensity is 100%. So oftentimes what chemists will do is they'll purposely scale everything so that their parent peak is set at 100%. But then if we look at the mass plus 1 radical cation, which obviously would be at a mass to charge ratio of 69, its relative intensity is now 4.3%. How many carbons are in this molecule? How many? 4? Yeah, so let's go through and quickly do the math. We know we've got 4.3 divided by 100 times 100 divided by 1.1. It's going to be about 4 carbons. Why isn't it exactly 4 carbons? Or 4, I should say. If we do the math, it's not going to be perfect 4. What do you guys think? Do we have any other heavier isotopes that might swing things a little bit? Yeah, we have a really small probability of deuterium atoms in there as well. So that's not going to make things come out to perfectly round numbers. What you will get is a number that's a very good approximation of your number of carbons. So let's do another one just for practice. So let's say we've got our parent radical cation at a mass to charge of 96. And let's say we've got our mass plus 1 radical cation at a mass to charge of 97. And let's look at their relative intensities. Let's say for our parent peak that we've now got a relative intensity of 19.0%. And for our mass plus 1 peak, it's now 1.5%. How many carbons would we have? So it'd be 1.5 divided by 19.0 times 100 divided by 1.1. I'll pull out my calculator. 1.5 divided by 19. I'm getting 7.1. I'll just call it 7.2. Keep our sig figs right. Approximately this means 7 carbons, right? So that's given us really useful information about our molecule in terms of how many carbons there should be in it just from the isotope pattern. You can quite often look at molecular weight and guess, but you don't know if there's oxygens, nitrogens, other things like that. In this one, do you think there's a nitrogen in there? What do you guys think?
Yes.
Is it odd? Is our parent peak odd? No, our parent peak is even, which means either we have 0 nitrogens or we've got 2, 4, 6, some even number of nitrogens. In this case, it would be probably most likely that there are no nitrogens, but we've gained some information there regarding number of carbons, potential number of nitrogens, and the overall mass of our molecule.
So I think an odd thing only applies to the parent one.
Only applies to the parent one. With the mass plus 1 peak, you're always going to run into odd numbers. So, yep. Let's take a look at the other thing that kind of throws people for a loop. Once in a while, we run into our parent peak, and then we run into peaks that are 2 mass units heavier. And this is a really, really useful hint. So let's take a look at these useful hints. This usually screams that there's some sort of halogen involved. Usually it means that there's a bromine or a chlorine involved. The question is, well, why is that the case? Well, if we look at chlorine, it's normally mass number of 35. This is 75.78% abundant. If we look at chlorine 37, this is 24.22. So we actually don't really have much of chlorine 36 around. It actually skips an isotope and jump straight up to isotopes where it's gained 2 neutrons. And if we look at this, this is a really nice feature, right? So we can say this is approximately a 3-to-1 ratio. So let's go and look down at something like chlorobenzene. If we look at this, we've got a mass plus 2, and this is roughly a 3-to-1 ratio. Usually the only time you see a mass plus 2 peak is when you have a halogen, and the intensity of these peaks is also pretty useful. So let's take a look at bromine's natural abundance. I'll give you guys a hint. If we look at our chart, what sort of ratio do you think it's going to be in for the mass plus 2?
3 to 1.
Well, let's look at it. We've got our parent peak on the far left. Mass plus 1 is the little one in the well, and then mass plus 2 is to the right. These are roughly equal, right? Which matches up really nicely with the isotope pattern for bromine. So if we look at bromine 79, it's got an abundance of 50.69%. Oops, this should be 79. And if we look at bromine 81, this has an abundance of 49.31% abundance. So whenever you see a 1-to-1 ratio for your parent peak for the compared to the mass plus 2, that's usually indicative of some sort of bromine being involved. I'm going to go off on a small tangent here. How many of you guys have watched the new Cosmos series? Neil deGrasse Tyson? Pretty cool guy. All right, so what I did, I guess before I say this, how many of you have Netflix or know somebody that has Netflix? A lot of people know somebody that has Netflix. On Netflix, you can watch these shows for free. There are also other ways to watch them. I'll let you guys figure that out. But what I did was I posted on the topic of the week a whole section on Claire Patterson. Has anybody ever heard of him? I know Jacob has. So Claire Patterson was a scientist that used mass spectrometry, and he was looking at isotope patterns in particular. And the cool thing that he did was he was looking at the ratio of lead to uranium in meteorites, right? So we can find meteors, and meteors are essentially leftover pieces of the formation of our solar system, right? So our solar system formed all at once. Some of that got turned into planets. Other fragments essentially got isolated in the cold of space as asteroids or comets, things like that. So he found these meteors, and they would drill in, and they would look for the ratio of uranium to lead. And why do you think that's a useful ratio? Does uranium hang out as uranium for very long? No, it decays, right? So if you think back to Gen Chem, that uranium will slowly decay all the way down to lead. And so by studying that ratio of uranium versus lead, you can essentially look at, all right, how much time has passed that's allowed this uranium to decay into lead? And from that, and some other isotope patterns, you can actually back calculate out the age of our solar system, which tells us the age of our planet. And this was pretty controversial for a few reasons. Obviously, the religious right didn't like it because some people on the religious right hold firm that our planet is less than 5,000 years old, which is kind of crazy. He calculated very, very accurately that it's 4.55 billion years old, and that number is held since the 1960s. And also, the really interesting thing that you'll see if you watch this is he had one hell of a time figuring out concentrations of lead. Does anybody know why?
Lead contamination.
Yeah, lead contamination. So we were pumping lead into our gasoline. We were painting our homes with it. We were coating tin cans with lead. Lead was everywhere. So he spent over a decade trying to figure out how much lead was in samples of meteorites. And you want to talk about frustration. That guy lived with frustration for a decade. And then once he figured out where the contamination was coming from, he waved his hands up and down and he was like, guys, we're poisoning ourselves. We need to get this lead out of our environment. At which point the petroleum industry told him to shut up. Otherwise, we're not giving you any more money and we'll destroy your career and make you look like a bozo. And he spent essentially his whole life trying to tell people that lead was bad for you, and now it's a commonly accepted thing. So Claire Patterson, you've never heard of him, discovered the age of our solar system and our planet, told us we were being poisoned by lead, created one of the best health reforms of the past 50 years, and he also developed clean room techniques that are used in almost all semiconductor manufacturing today. So one scientist did a whole lot of work. Basically, that was the result of sheer frustration. So frustration can be a very powerful, useful motivator, right? So don't look at frustration or failures as negative things. We've got to look at frustrations and say, what happened? How can we fix this? How can we move on from this? Because oftentimes that's how the best discoveries are made. I'm going to kind of leave it there. And stop by my office if you guys have any questions.